So from the earlier model, we can convert it to this model. So I'll say B1. B1. And so when you want to replicate, you can go for this 3D view and select all these and replicate at 3.6 14 times. And then take this part and replicate other 14 times. So you can create this building having 30 floors. And so I'll save this as BU2. Save. And if you look at here, there's no coupling action. And here also, you see there's no coupling action. Only a small beam is connecting. So without any coupling action, we have got this model. And before you analyze, you have to look at the ground level and make sure all the points at the ground level are marked as a support condition. Because earlier we did not have these supports. We added them later. So the moment you do this, you can see whether there are any loose ends that are not provided with supports. So you have to check that. And also we need a small correction for this slab self weight, which I said 4.2 because the slab thickness is 175. And also load patterns, this wind load has to be defined as a wind load. Okay, so now we can run and see what are the properties we get. And if you look at the mass source, so far I have not defined the mass source properly. We'll do that later. First, I'm running it only from the elements and additional masses, nothing from the loads. So we see what the answer that we get. So we can ask it to analyze. So once we analyze the structure, here you can see the first mode, 3.35, second mode 2.86, third mode 2.79. So if I look at the top of the structure and ask it to display. So if you look at the deformed shape due to dead weight, you can see it shows some turn, but if you look at the values, you can see the values are all U1, U2, U3. U1 and U2 all are 0.0002, which means, although this program shows a big deformation, the deformation is almost zero. It's 0.0006 meters, which means it's less than 1 millimeter deformation, although the program graphics show a big deformation, but the actual deformation is very small. And then we can ask it to show the deformed shape and the model and ask it to start animation. So now you can see the second mode is a torsion mode. Third mode is a mode that moves this way. So this is the first mode. So you can see although this is a shorter dimension, this is a longer dimension. The building is stiffer in the shorter direction than this direction. So generally the building behavior will be other way around. Building will be more flexible in the shorter direction and stiffer in the longer direction. But in this particular building, these walls are 6 meters long and these walls are only 2.5 meters long. So these walls are only 2.5 meters long. So because of that reason, the building moves this way more than this way. So that is something that you can find in our building because it's having only 4 frames in both directions. So the smaller dimension looks stiffer. So then you can also see now the mass was not defined properly. Mass was defined only as the mass coming from the slabs, beams and columns and the shear walls. So what we can do is we can define the mass source and say it comes from all this. So we have to say consider dead and sorry, we should not consider dead from elements and additional masses and loads. And for unit slab 1, I would say that we are having finishers of 1, which is say finishers is 0.7, although we allocate 1 kilonewton per meter squared. Finishers is 0.7, and then we'll also get the services as 0.3, and then partition load of another 0.7. So it's 1.7. So we are saying in addition to the elements, consider loads, consider the unit slab load of 1.7, and for unit slab 2 I will allocate 1. That is whatever the loads that coming from, or I can say 0.7 or 1, because that is the load coming from finishers and services. So I'll add that also. So you get unit slab 1, unit slab 2, and I'll say okay. And let's run it again and see what happens. Now here you can see some change, and now you can see you get a higher value because the weight is more. Weight is more. So you get 3.65 seconds, and so you might also say that this is not a very rigid structure because our shear wall lengths are not very high. And so 30-story building having a natural period of vibration of 3.65 in one direction, 3.1 in the other direction. So this direction where we get 3.65 is somewhat flexible. The general rule for natural period of vibration is 0.1 seconds per flow. Did you know that rule? Have you come across that rule? Generally, the natural period of vibration is about 0.1 seconds per flow. That's a general rule. Have you come across that rule?
Yes, sir. We studied this semester. Sujiva sir taught.
Yeah. So that is about 0.1. So when you use that that particular rule, you should get something like 3 seconds. But here you can see we are getting values slightly above 3 seconds. And you can also see when you allocate the correct mass, the natural period of vibration changes. But if you look at the modes, so I'll go to the top again, or I can even start animation, but it might take little time. So this second mode, so this is the first mode. This is second mode. This is the third mode. That is the fourth mode. And if you look at the modes again, first mode, second mode is the twisting mode. That is the third mode. That is the fourth mode. And fourth mode, you can see 1.16, which means that mode might not happen easily, although it looks realistic, but it might not happen that easily. And the other modes would be with the dominating modes. Right. So that is 3. So now you can see the effect of this mass. Now save it, and I'll save it as 3. And then what I'm going to do is I will convert this this small beam to a coupling beam. So I'm going to view here. and this beam is very small. I see it's the additional beam. So what I do is I will replace all these beams by this beam. That is 1200 by 300 beam, because I said that, outer walls I considered as 300 millimeters of thickness. So I will, and the floor height is 3.6 meters, and the entrance to the lift lobby, 2.4 meter height is sufficient. So the rest of the height will be a coupling beam. So the size is 1200 by 300. So there I can allocate the same size for all the others. Sign, frame, same thing. And do the same for all. There's some area that I have not allocated. And assign. Okay. Now all these beams are coupling beams, so I had to do the same thing for the other frame. And for that, I'll say, go there, and assign frame sections. Okay. So now these beams are strong, and we'll analyze it and see what happens. Now you can see the effect of coupling action clearly, and you can see that the natural period of vibration has reduced from 3.6 to 3.15, and that is, can you see this change, significant change due to this coupling beam? Any feedback?
Yes, sir.
Yeah, you can see that, there's a very significant reduction. And then we'll also see the force mode. we see that we are looking at the top of the building and display deform shape model 1. So that is the first mode. The second one. Now you can see that's the torsional mode. And if you look at the torsional mode, it's far away from the, you can see the torsional mode is far away from the other two modes. Earlier, second mode was torsional mode. Now you can see the torsional mode has moved away and the coupling action has significant effect because this will act like a closed box. It will act like a closed box. When you have that type of coupling beam connecting the two walls. And if you want to make it even stronger, you can have another beam here, right? You can have another beam there as well. So if you want, you can have a quick look at that. But that effect will be lesser. The reason is, the shear flow will take place around the core. So the effect of this one will not be that significant, except for the deflection. To control the deflection, this can be useful, but I think this may not be that effective in control controlling the way that the building is going to vibrate. So as an exercise, we'll have a quick look at that as well. So we say save, and I'll say save as BU3A. I just don't want to upset the earlier versions that I have saved. And so now what I do is view. We'll see what will happen if we, now there's no beam, and if we cast a beam there, we put a beam here and select, replicate 29 times. So it's done, and I can analyze it. Now you can see there isn't much effect, very marginal effect due to that. And now you can clearly see that the modes have not changed, and this particular coupling beam has not much effect on the dynamic properties, but it might have some effect on the deflection. So that. So any question up to now? Any question up to now? Then we'll move to when you run the analysis, always when you move into a new one, just remove the analysis part, because this analysis creates a lot of large files that can fill up your hard disk. So all open. Four. Not much difference. Five. Again, not much difference. 1, 6. Right. So now earlier I have shown you that how to model only the superstructure. Now we are trying to see how to include the substructure also into the same model, so that you'll have both superstructure and substructure together. And so how you model this is so do a very quick demonstration on this. And so now we like to see some pile foundation for this structure, and to get some idea about the foundation conditions, we'll open 3A and we'll ask it to analyze it. And define node combinations, go into service, envelope XY, and we'll view undeformed shape and view at the ground level, and we'll ask it to display the forces of the joints due to the service envelope XY. Right. Now you can see the values. And here the values are something like 7,266, 9,663, and so on. Only thing is we have not applied the wind loads. So when you apply the wind loads, these values can increase. So if you take one of these, the load is about 11,788, and here you get 12,000 kilonewtons. So the chances are that if you are going to provide 4 piles, we should be able to manage it with about 1,000 millimeter diameter piles. We'll be able to manage it with about 1,000 millimeter diameter piles. So let's assume that we are going to use 1,000 millimeter diameter piles, and If you are having 1000 diameter piles, then when you have the column, we can have the piles located like this. And the distance between the piles will be 3 times diameters. Sometimes, we go for 2.5 times diameters as well. But 3 times diameters is preferred. If you can provide 3 times diameters, better to provide 3 times diameters. But if you can't provide 3 times diameters, provide at least about 2.5 times diameters. And I explained the other day, if you are having end-bearing piles, you can go for 2 times diameters. Whereas when you have friction piles, it's better to go for 3 times diameters. So if you are going with 3 times diameters, then the distance between two centers will be 3 meters and 3 meters. And the pile D has 0.5 meters here. And the pile cap will need a minimum of 150 millimeters to bend the reinforcement and anchor it. So the bottom reinforcement has to be bent and anchored. So this distance will be 0.65 meters. So you need to have something like 0.65 meters extra. So what you do is, so we'll move to open. So if you are having loads like 12,000, in excess of 12,000, the piles may need a capacity like 12,000 divided by 4 is 3,000. So with the self weight of the pile and pile caps and all that, you will find that the pile loads can be around 3,500 kilonewtons. So 1 meter piles can easily take about 3,500 kilonewtons. So generally 1 meter diameter piles can go up to about 4,500 kilonewtons. So 1 meter diameter piles are sufficient, and we are going to consider providing 4 piles at each column location. So what I do is I'll open this one. And view. Now we have to create these 4 piles at a spacing of 1 meter. So what we can do is we can draw this additional beam, and I'll say 6A where 6A. So you can say additional beam. So I can say that replicate at 7.5 plus, 1.5 plus 0.65, that is 8, 9.65. and this minus 4, and do minus 3, and I can ask it to replicate 0, 65, set 31, and ask it to replicate again at minus 3, and replicate minus 0.65, and also this one to replicate at 5 meters, and this is minus 8.15, so 6, and replicate at 0.65, replicate at 3, and replicate at 0.65, and then divide frames, break at intersection, and then we can extrude these 4 points. Extrude points to frames, pile cap, pile 1000, 0, minus 20, 1. So those are the piles. And we say assign, joint, restraints. Okay. And then we have to define the pile cap. And for that, okay, I have defined this pile cap earlier. And say divide. So you can just allocate this. Okay, like that. So, and after that, you have to get rid of this particular support. And the important thing is that the important thing about this is the connectivity. So you can see that the column is connected to the pile cap. Column is connected to the pile cap at a node, and piles are also connected to the pile cap at a node. So these are all node points. So this way you can ensure that there's proper connectivity between the piles and the column, where all are combined together by using the pile cap. And then you can actually refine this if you want, and you say edit areas and divide the areas into further 2 by 2, and you will get a finer mesh, and that way you can get better results. So this way you can create the pile cap, and once you create one pile cap and the piles, you can highlight all that and put there, select all the members, and then add pile caps at all these locations, 1, 2, 3, 4, replicate at a spacing of 6, 4 times, select a previous selection and replicate this way 6 meter interval. So the pile caps can be generated that way easily, so that the whole building can be put on piles. So we'll have a look at BO 7. Now here you can see I have actually allocated piles. Yeah. View, display options, fill object. Now it's clearer, and you can see all the pile caps. And what I have done is, there's a column here due to that 3.6 meter long shear wall. So I have created 2 more piles here. And here at the end of each shear wall, I have created a pile. Sometimes these piles may not be sufficient because some of these loads can be higher. In that case, you might need additional piles or a larger diameter pile. So even with the problem with very large piles is when you try to maintain the center to center spacing, you will find that 3 times rule cannot be maintained, and so some geotechnical consultants do not have a big issue with large diameter piles. Say when you use something like 1.2 meter piles, then the center to center distance with 3 times diameters is 3.6 meters. Then what is the clear spacing between 2 piles? the clear space in between two piles will be 2.4 meters. So the chances of the drilling operation of one pile damaging the other pile is very remote because the gap is 2.4 meters. So whereas, if you go with 2.5 times diameters with 1.2 meter, and when you deduct 1.2 meters, still you get a gap of 1.8 meter. So when you have a gap of 1.8 meter, the drilling operation damaging another pile is also very remote. So if you have predominantly end-bearing piles, then you can actually go for something like 2.5 times diameters. Whereas if you are mobilizing significant level of skin friction, then better to go for something like 3 times diameters as well. So it's up to you. But in this area, sometimes the 1 meter diameter pile may not be sufficient. But for the time being, I have allocated 1 meter diameter piles. Then you'll ask, what are these? What are these? So I will explain all that after taking a break. Is it okay?